Welcome back to Discrete Math. I'm Dr. Jeff Groh. We'll begin today's discussion by talking about relations. What is a relation? Between a set A and a set B is any collection of ordered pairs. Is a collection of ordered pairs, so something of the form ordered pairs, a set of ordered pairs where A has to lie in the set A and B lies in the set B. Ordered pairs can be graphed like points on a chart. So for instance, if I have an oval like this, that is a relation. Even if I were to fill the oval in, it's still a relation. Because a relation is just a set of ordered pairs. So if I want to do something like this, that's a relation. Here's another example. Suppose I have R, which is 1, 2, 2, 4, and 2, 5. These points here. Just those points. 1, 2, 2, 4, and 2, 5. It's just a collection of ordered pairs. This is the graph of that relation. Next, we're going to discuss what a function is. A function, and we'll call it a fancy f, is a relation. So in other words, a function is a collection of ordered pairs, but it has another restriction. Functions have to satisfy the vertical line test, such that if x, y1 and x, y2 are elements of this function, which is just a set of ordered pairs, then if these have exactly the same x coordinate, then they can't have different y coordinates. They have to be the same. So in other words, if at x you have some y1 and y2 that are different, that's forbidden for functions because that would fail the vertical line test. It would intersect the graph more than once. So an oval like this is not a function because it doesn't satisfy that vertical line test. But it is a relation. There's a notation. Let's suppose that f is a function and some point xy is an element of this set of ordered pairs. We usually write y equals f of x. So just because the point xy is in here means that associated with this x we have this y. And this notation is kind of like the meat grinder version of functions. You have an input where x's go in. It goes around and around inside the function and then gets spit out as a y. We think of the parentheses as like the input slot for the x, goes into the function and then plops out the y. Note, functions are also sometimes called mappings or transformations. Also, if f is like this, we often say, let's suppose x is in A, y is in B. We write f maps A into B, and that's how we read that. F maps A into B. The domain of a relation is the set of all x such that the point xy is an element of the relation for some y. So another way of thinking of it is that the domain is the set of all into a function, but the notion of domain is a little more general and applies to relations as well. If f maps some set A into some set B, then A is the domain. We call B the codomain. It's a little bit different from the range. The codomain is the set that outputs come from. However, we could have something like f maps the real line into the real line and define f of x to be x squared. But the codomain is the set of real numbers. That's not the range, because when you plug a real number into the square function, it makes it non-negative. You can't get negative numbers out. So the range and the codomain are slightly different concepts. The range of a relation is the set of all y such that xy is an element of the relation for some x. So the range is everything that actually comes out. So if my function is f of x equals x squared, the domain, let's say we're restricting ourselves to real numbers, is the entire real line. The range goes from 0 to infinity. It doesn't output negative numbers. Functions f and g are equal if f equals g as sets, if they're equal as sets. In other words, if they have the same points. Alternatively, we could require that these have the same domains and codomain, and f of x equals g of x for all x that are in the domain. Let me give you an example. Suppose f of x is the square root of x squared, and g of x is x if x is bigger than or equal to 0, and negative x if x is less than 0. Now, you might remember that the square root of x squared is the absolute value of x, not x. You can see if I plug a negative 2 in for x, Square has the priority. You get positive 4. And then this symbol, it's not just any square root, it's the principal square root, which is always non-negative. So the square root of 4 will be positive 2, not plus or minus 2, 2. So if x is equal to negative 2, and I plug it through this function, I end up with positive 2 coming out. I can't get negative things out because I'm using the principal square root, which gives me positive roots only. And so here, f equals g. These functions are equal. This also describes the absolute value function. Computer programming languages often require that you declare the data type for both the domain and the codomain of any given function that you program. Suppose I define my function to be f of x equals x squared, but I make my domain the set of integers. Let's make our codomain also integers. The range will be 0, 1, 2, and so on. It won't include negative integers, only non-negative integers. A function is called real valued if its codomain is the set of real numbers. It is integer valued if the codomain is the set of integers. Complex valued if the codomain is the set of complex numbers. How do we add two functions? By evaluating them separately and then adding. Same thing with multiplication, subtraction, division. They're defined in this way. As an example, if f of x is x squared plus 1 and g of x is 2x, then f plus g of x will be x squared plus 1 plus 2x. In our next definition, suppose f maps A into B, so we have a domain of A and a codomain of B, and let S be a subset of A. The image of S under F is, it's the set of all y such that y equals f of x, where x is an element of the set. So it's the things that plop out when you plug things from S into the function. As an example, suppose A is the set with the letters A, B, and C, and B is the collection of numbers 1 and 2. We'll define a function so that f of A is 1, f of B is 1, and f of C is 2. Then, let's set S to be the set AB. F of S will be the set of things that come out when we plug A or B in, but only one comes out. So that will be the image of this set under the function f. A function f is said to be one-to-one or an injection. Those will mean the same thing if the function satisfies the horizontal line test. If whenever x1 is not equal to x2, where x1 and x2 are in the domain of f, then f of x1 if we have different points in the domain, then you'll have to have different outputs as well. So here's an example of a function that is not one-to-one. There's an x1 over here and an x2 over here. They're distinct, and yet they have the same y value. The y values are equal. So this is not one-to-one, and it gets tedious writing out one-to-one, so we often write 1-1 when we're saying it's one-to-one, or when we're implying that it is an injection. So we have to satisfy the horizontal line test for one-to-one functions. They have to satisfy both. The vertical line test to be a function and the horizontal line test to be one-to-one. So something like this would be a one-to-one function. Another way to state that a function is one-to-one is that if f of x1 equals f of x2, then that implies x1 equals x2. This is very useful when solving certain that involve one-to-one functions. Is f of x equals 3x plus 2 one-to-one? Well, let's try this out. Suppose f of a, that's 3a plus 2, equals 3b plus 2, which is f of b. Does this equation imply that a equals b? Well, yes, because you can subtract 2 from both sides, and then divide both sides by 3. So yes, it is one-to-one. It is an injection. In our next definition, we're going to suppose that the domain and codomain are subsets of real numbers. So let f map a into b These are sets of real numbers. We say that f is increasing on the set A if whenever x1 is less than x2, that implies f is less than or equal to f of x2. That's what it means to be increasing. It is strictly increasing if x1 strictly less than x2 implies f of x1 is less than f of x2. So a function that is constant, where given an x1 and an x2, you have the same y values, that could be described as increasing, but it is not strictly increasing. To be strictly increasing, you have to go up as you march from left to right. Increasing is always measured as you march from left to right on the graph. There are obviously corresponding notions for functions that are decreasing and those that are strictly decreasing. In this next definition, we'll let f map A into B. We say that f is onto or a surjection if for each element of the codomain there exists something in the domain such that f of a equals b. So an example of a function that is not a surjection might be y equals x squared. Why is it not a surjection if f maps the reals into the reals? Because you don't get negatives out. You can choose -1, and there will not exist some real number in the domain, so that you square that real number, you'll get -1 out. So when you're talking about surjection, x's and y's go over here. To be a surjection, the entire codomain has to be reached by some value in the domain. Let me give you another way of looking at this. If the domain is ABC and the range is 1, 2, this would represent f mapping, our function mapping A onto 1, B onto 2, and C onto 2. This is not 1 to 1, but it is a surjection, i.e. it's onto, because everything in the codomain was mapped onto by something from the domain. If I have A, B, 1, 2, 3, this is 1 to 1, so it is an injection, but it is not onto, so it's not a surjection. There's this number 3 that didn't get reached by something in the domain. If you consider f mapping R into R defined by f of x equals x cubed, then this thing looks like this more or less. It is both, well, it satisfies the vertical line test, so it's a function, satisfies the horizontal line test, so it's 1 to 1. And it maps onto all y values. Every y value is hit, so it is also onto. It's both an injection and a surjection. A function that is both 1 to 1 and onto is called a bijection. So bijections have both properties, 1 to 1 and onto. By the way, it is through bijections that we come to understand the notion of number itself. Suppose I have some sheep. And these are my white sheep, and then I have black sheep. I guess they should probably also have legs. Now I can make a bijection, a mapping that is 1 to 1 and onto, from the white sheep to the black sheep. In fact, I can make a bijection between the white sheep and 3 fingers. First, second, third. Same thing with the black sheep. It's by making these bijections, usually to begin with our fingers, that we come to understand the notion of number itself. The identity function on a set A is given as follows. Whatever you plug in, it plugs the same thing out. So its domain is A, its codomain is A. And whatever you plug in, that's what it plugs out. So it's like the function y equals x. Every relation has an inverse. Let R be a relation. just a collection of ordered pairs. The inverse relation are with a superscript of -1. It's the set of all points yx such that xy is in the relation. So the inverse relation just reverses the x's and y's. Graphically, here's a relation. This would be the graph of the inverse relation. Switching the x and y's gives you this. And this particular example is kind of illustrative of an important idea. This function is not one-to-one. And so its inverse relation is not a function. It has an inverse relation, just not an inverse function. There's a theorem. You can see this theorem from the last example. The reason why the inverse relation was not a function is that the original function was not one-to-one. So here we'll let f be a function, and f inverse, its inverse relation. Then f inverse is a function if and only if the original function is one-to-one. So only one-to-one functions will have inverse functions. So if our function is described as f of x, the inverse function will be denoted with a superscript of -1. As a picture, if this is the domain and you have some x over here, the function maps that x over to some y. The inverse does the opposite. It maps that y and it outputs an x. Also, if y equals f of x, then f inverse of y equals x. This last formula gives us two other formulas if we think about it. If f acts on some x, it will send it to some value y, but the inverse will send it right back. And this is a function composition. Same goes through the other way. In this next example, suppose our relation has the points 1, 1, 1, 2, and 2, 3. You can see we have the point 1, 1, 1, 2, and 2, 3. This is obviously not a function. Regardless, every relation has an inverse relation that you get by simply reversing the coordinates. So if this is our relation, then our inverse relation has the point 1, 1, the point 2, 1, and the point 3, 2. The fact that inverse relations simply reverse the roles of x and y yields a strategy for solving for inverse functions. Suppose I have the function y equals 3x plus 2. How do I find my inverse function? Well, the inverse is what you get when you swap the roles of x and y. So we'll swap x and y, and then solve for y. So we'll have to move the 2 over, and then divide the 3 off. That is the inverse function. A function is said to be invertible if its inverse exists, is f of x equals x squared invertible? And the answer is no. The function does not satisfy the horizontal line test, so it's not one-to-one. So it is not invertible. However, if we make a domain restriction, now the function looks like this. And it is invertible with this restricted domain. You can find it by doing the following: swap x and y, and then solve for y. We do that with the square root. So if you take the square root, the square root of y will be y if y is positive, and y is always positive for this function and this domain restriction. Concerning function compositions, we usually think of it like this. We have g acting first and then f in this particular instance. And so let's suppose g maps over to here. This element of the range of g must be in the domain of f to output something else. So we may have different sets, A for the domain of g, B for the codomain. The codomain has some range inside of it, and then that range has to be in the domain of the function f in order for it to output anything. So you can see it can be possible to have f composed with g defined, whereas g composed with f may or may not be defined. If you have f going first and then g, that may not even make sense. One thing you should be aware of is that none of the trig functions are one-to-one, so none of them technically have an inverse function. So you may be wondering why we have these buttons for inverse sine, inverse cosine, inverse tangent on our calculators. And the answer is we have to make domain restrictions in order for there to be some little interval where the function is one-to-one, where it will have an inverse. As an example, suppose we have f of x equals, I don't know, how about sine of x, and g of x equals x squared. What is f composed with g of x? Well, by definition, it's f of g of x. So it's, since g of x is x squared, we'll plug x squared into this function. That gives me the sine of x squared. In the last example, if we compose the functions in the opposite way, f of x was sine of x, and then whatever goes into the function g gets squared. So it's sine of x quantity squared. By mathematical convention, it is customary to write this as sine squared x, like this. This is by a convention. It's an arbitrary choice made by some mathematicians in the past, that you can simplify writing expressions like this as just something like this. Suppose f has domain D and range R. We said earlier that f inverse of f of x equals x, so we can write the following. When you compose f inverse with f, you get the identity function on the domain of f. If you do the composition the other way around, you still get x, so you will get an identity function, but this time it's on the range. Remember, the inverse reverses the roles of domain and range. The domain for f becomes the range for f inverse. The range for f becomes the domain for f inverse. And so this will be the identity on the range. Sometimes we say that the graph of a function is the set of points x and y such that y equals f of x. So in other words, it's just the collection of points. It basically is the function itself. The floor function is the greatest integer less than or equal to x. We call this the floor function, and if I were to plug in something like 2.1 into the floor function, it outputs 2, the greatest integer less than or equal to what you plug in. If I plugged in negative 1.4, it would give me negative 2. It has to be something less than or equal to the number that you have on the number line, so you have to go to the left on the number line. Even for the negatives, keep going to the left, you'll get negative 2 in this case. You might have guessed that since there's a floor function, there's also a ceiling function. It's the least integer, the smallest integer, greater than or equal to x. So, for instance, if I plug 1.7 into the ceiling function, it'll output 2. It's easy to produce the graphs of these functions. Let's do the floor function here. Anywhere between 0 and 1, it's going to output 0 until it gets to 1, where at that point it's going to jump up. It'll make its next leap at 2, and so on. Whereas the ceiling function gives the least integer bigger than or equal to, so at 1/2 it'll have to output 1, but at 0 it'll have to output 0. And it keeps going like that. In our next example, I'm going to ask how many bytes are required to store 100 bits. You might remember that a byte consists of 8 bits. So if I have 100 bits and it's 8 bits per byte, I should have 100 divided by 8, but that 8 doesn't go evenly into 100. This is what, 12.5? And I don't have half a byte that I can contribute. So in other words, our answer is going to be the ceiling function of 100 over 8, and that will be 13. It takes 13 bytes to store 100 bits. There are some important properties for the floor and ceiling functions. First, if I have the floor function of negative x, that will output the negative of the ceiling function of x. What about negative x plugged into the ceiling? That's the negative floor function of x. Clearly, if you take the floor function of x plus n, where n is an element of the set of integers, that's going to be the same thing as the floor function of x plus n. The rounding can only happen from what results from here, not from the n. And the same holds true for the ceiling function. As long as n is an element of the set of integers. In addition, there are some other properties of the floor function. X minus 1 is always less than or equal to the floor function of x. And the floor function is less than or equal to x. But x is less than or equal to the ceiling function. And finally, the ceiling function is strictly less than x plus 1. When does the floor function of x equal n? Only when n is less than or equal to x is less than n plus 1. We're assuming, of course, that n is an element of the set of integers. So if the floor function outputs an integer, which x is, n will be greater than x minus 1 and less than or equal to x. What about the ceiling function? What if it outputs some integer n? That's only if x is greater than n minus 1 is less than or equal to n. N is greater than or equal to x, and that's less than x plus 1. Next, I want to prove that the floor function of 2x equals the floor function of x plus the floor function of x plus 1/2. So in our proof, I'm going to let x be n plus a little bit. We're assuming that epsilon comes from the set 0 to 1. So x will be no smaller than n and no bigger. It'll be strictly less than n plus 1. So the floor function will output n. It'll ignore this small little number between 0 and 1. Now let's look at the floor function of 2x. Well, twice x, that's going to be twice n plus 2 epsilon. And what it outputs will depend upon the value of epsilon. If epsilon is less than 1/2 but bigger than 0, then this part will be less than 1 and it will be ignored by the floor function, so we'll output 2n. But if we go bigger for this epsilon, then this becomes bigger than 1 and we end up with 2n plus 1. Let's look at the floor function of x plus 1/2 for this x. What you get depends upon what this epsilon is again. You're going to output n. But you'll output n plus 1 if epsilon is between 1/2 and 1. So look what happens if you add the floor function to this function, the floor function of x plus 1/2. If you add them, you'll have 2n here and 2n plus 1 here, just like you have 2n here and 2n plus 1 here. So by adding these, we can see that the floor function of 2x is the floor function of x plus the floor function of x plus 1/2. Prove or disprove. Is the ceiling function of x plus y equal to the ceiling function of x plus the ceiling function of y? This seems a rather dubious proposition, and it's easier to disprove something than it is to prove it. To disprove some equation like this, all you have to do is provide one counterexample. So let's look at the ceiling function of 1/2 plus 1/2. 1/2 plus 1/2 is 1. The ceiling function is 1. But if we look at the ceiling function of 1/2 plus the ceiling function of 1/2, the ceiling function of 1/2 is 1, and then 1, I get 2. So the ceiling function of 1/2 plus 1/2 is not the ceiling function of 1/2 plus the ceiling function of 1/2. And so it's false. We will study a lot of different functions like logs, exponential functions, polynomials, but there is an interesting convention in your textbook that's different from many other textbooks. A lot of times when you write log x, you mean log base 10, but our text means log base 2. I guess it presumes that if you're a computer scientist, you're going to be interested in log base 2 for the most part. So unless otherwise noted, we'll assume that the base is 2. You'll need to know about factorials. So 0 factorial is, because I said so, 1. Usually n factorial would be n times n minus 1 times 2, all the way down to 2 times 1. It's the product of the natural numbers down to 1. So 3 factorial would be 3 times 2 times 1, or 6. Note that factorials grow very rapidly. Try to calculate 100 factorial, for instance. Seems like a very mild number, but a lot of calculators can't handle numbers this large. Stirling's formula gives us a way of estimating n factorial. It's approximately the square root of 2 pi n times n divided by e to the power n. And in particular, this squiggle here, the tilde, will mean that it's asymptotically, it goes towards this, in the sense that if we take the limit as n goes to infinity, the ratio between these two they go towards 1. So the approximation gets better and better as n gets larger and larger. To this point, we've allowed the codomain and range to be different for a given function. You can do the same thing with the domain, but you'll have to define something besides a function. We'll call this a partial function. Partial function from A into B has domain D, which is contained in A but not necessarily equal to A. So for example, if I have the function 1 over x squared, note that this function is not defined at 0, but we can still call this a partial function from the entire set of real numbers into the entire set of real numbers. It's just the domain is not the entire set of real numbers. The domain is all real numbers except 0. So the domain is all real numbers except 0. R is a set of real numbers, and you have to subtract things that are of like kind. So you have to subtract a set the set that contains 0. So that removes 0 from the domain. But we can have a partial function from R to R defined in this way.